Okay, I'm going to talk to you about this chapter here, this unit, Boolean Logic 2.4. Most likely there will be questions on it. There's usually questions on every single one of these topics. It's a really short one, so let's have a look at it. Here's the spec, and it says that you've got to do simple logic diagrams using operators and, or, and not. Truth tables, combine Boolean operators using and, or not, and applying logical operators in truth tables to solve problems. Sounds complicated, but it's not too tricky. So what you need to know about is you need to know about what a logic gate is, and you've got the three, so you only need to know three. They are listed here in the spec. These are called logic gates, and they are part of circuits, and each line represents and on the left hand side represents an input, so electricity going into it, and then this line is the output, so what comes out of it. Now each of these different logic gates do something slightly different. This one, I should actually probably go to this slide here. This one here is called an AND gate, and it needs electricity going into both of these points for something to come out. How do these relate to computing though? So they are basically in the CPU in circuit, as part of a circuit, and they test logic for us. So you know when you're programming and you have an if statement which says if x is greater than 10 and x is less than 20, do this. Well, that will check it for us because that's the first condition, that's the second condition, and this is if it's true. So this one here is an OR gate. So with this one, the rule has to be that just one of these has to have be positive, has to be true. So one of these has to have electricity going into it. It could be that both of them do, or it could be that just a single one of them does for something to come out. A NOT gate just reverses what goes in. So if something goes in this side, electricity, if this is true, that's going to be false. Okay, let's just go a little bit of a step back, and I just want to talk about this. Why do we use binary in computers? A computer is basically a collection of transistors, like switches, and circuits, and those components have two states. So in a circuit you've got electricity going round or not, and with a switch, a transistor, it can either be on or off, which is how you can store like the state of something, whether or not it's a 1 or a 0 in binary. So that is why we use binary. That does come up actually occasionally. You get the question, why do we use binary in computers? Just mention transistors or switches. You could talk about ones and zeros being on and off, and you'll get all the marks just for that. I've mentioned the three gates. I've told you what they do. So, do you remember that spec point about truth tables? This is a truth table. It shows you every possible combination of every possible combination of inputs and what the corresponding output would be. So here you have an AND gate. A and B are the inputs, Q is the output. So you put in all the possible combinations. I usually go like kind of almost as if I'm counting in binary, 0, 1, and then 2, and then what would be the equivalent of 3 in binary. That makes sure that I get all the possible options if I do that. And the only one which is going to have an output is the 1 and the 1. There we go. You can see these logic gates and logic circuits expressed as a kind of equation, and this is what it looks like. The output goes on the left, and then the inputs go on the right hand side, and the exam board will use the full word. You do see notation at A level, but the exam board should use the whole word, so and, or not, and here. So you could get given one of these and asked to fill out the truth table. You could get given one of these expressions and asked to fill out the truth table or draw the diagram. The other thing you might get asked is to write the expression for a diagram. If it's a single gate, it's not too bad, is it? but it might be that they give you something which contains more than one logic gate, which we'll look at in a minute. Here's an OR gate. So with an OR gate, remember I said there has to be some electricity going into one of the inputs for there to be an output. There it is. NOT gate reverses it. Because there's only one input, there's only two possible states for that input, two possible outputs. Okay, so this notation, notation like expressing OR gates as a kind of equation. That is it. We've talked about that already. Now we're talking about combining multiple gates to create a logic circuit. Here's an example. Combining two AND gates. You've got an AND gate. One thing that I always think of when I'm trying to remember what symbol does what, I just think, well, the AND gate looks like a big D. And then the NOT gate, you can remember that one, the triangle with the little circle. And then the OR gate is kind of like a moon. That's what I think of it, like a crescent moon. But you will probably have your own way of remembering it, but maybe that might help. Okay, so combining two AND gates, here we go. We've got three inputs, A, B and C. A and B go into this AND gate and then come out as D. Now the truth table for that is a lot bigger, isn't it? Because we've got three inputs, which means we're going to have 8 rows. There we go. 0, 0, 0, 0, 0, 1, and so on, and it goes up like that until we get all the combinations. We've got D here, and we've got D equals A and B. Perhaps should have put AND in there to make it easier, but that's the AND symbol. So what you have to do with this one is you have to look at where A and B are both ANDs, which they are here. That will result in a 1 coming out of D, and then you can compare D and C, and there's only one combination of inputs that results in a output. This is what that's expressed. This is what it is in notation. This one, you've got an OR gate going into a NOT gate. So one of these A's or B's has to be a 1 for C to have current going through it. And then the NOT gate is going to reverse that. So let's have a look. 0, 0 is not going to result in anything going into C. So that, funnily enough, is the only one that will actually get an output, because remember, NOT reverses it. These others, there's something going into the OR gate, so the C can be set to true, which means that the output's 0 because that's reversed. I'm not going to worry about that because that's not actually how the exam board expresses Boolean algebra anymore. They use full words like this. You see this just here. So let's look at this one. Oh, I've put the mark scheme. I forgot to hide the mark scheme, but anyway, it doesn't matter. Right, so we've got A and B or C. So we've got 3 inputs. The first thing we've got to check is A and B to see if any of those are both 1. They are at the bottom here, or C. So what you would then do is you would look at, this is a bit trickier because we haven't got that middle value looking at A and B, but we know that this one is going to end up with a 1, this one's going to end up with a 1, everything else is going to be a 0. You could actually write that kind of in there, and then what you would do is you would look to see whether or not that result of A and B is a 1, and if it is, P is going to be a 1, or anywhere where C is a 1 is going to be a 1 as well. And that's the answer. Now this one, you've got to draw it. So it says P, which is the output over here, not A and B or C. So because there's 3 different like Boolean operators in that, not and or are all there, the indication is you're going to have a gate for each one. I would look at what's in the brackets, B or C, and I would draw that OR gate in. Not A means that we've got to put a NOT gate pretty quickly to reverse A, and then the operator that joins those 2 separate parts of the equation is AND, so you've got an AND gate running there at the end. Here's another example from the last couple of years. You get given an expression here, so you're not A or B and C, and you have to fill out the results. So it wants you to put in the possible options for A. Well, that's going to be all ones, but just count up in binary again and then work out what the output's going to be. So it's not going to be A, so wherever there is an A, we're going to have a 1. Wherever there's a 0 even, it's going to result in a 1 coming out of that NOT gate. And then we've got A and C, so you'd be looking at where there were 1s in both of these. And then you have to look at the OR gate. So anything that resulted in a 1 here, with an OR gate, you've got a 1 going into it, which means you're going to have an output of a 1, which is what we've got there. So look at this type of this question. Now this is a little trickier because it's a scenario, so you've got to try and work out how this could be tested, this scenario could be tested with a logic gate. I'll move the answer down a bit. A garden floodlight system uses inputs from sensors and switches to decide whether it should be turned on. The table shows the inputs into the system and the meaning of each input. So we've got A, which is the motion sensor, B is a light sensor, and C is a light switch. The input of 1 is that motion is detected, and with B you get a 1, light levels indicate it's daytime, and the switch is turned on. The floodlight is designed to be on when the switch is turned on and the motion sensor detects motion at night time. Right, so when the switch is turned on and the motion sensor detects motion at night time, draw a logic diagram for the floodlight. So A is a motion sensor. The light sensor indicates it's daytime. So if the light sensor's on, we don't want the floodlight to come on, do we? So if the light sensor is true, we don't want it to come on. Okay, let's have a look at what we've got here. It's very difficult to see it, but there are different ways of doing that. So B was the light sensor. So if the light sensor is on, we're going to it reverses that to a 0, sends the 0 into an AND gate, so there's no way anything's coming out of that, which then would send a 0 into this AND gate, which means that you're going to result in a 0, which is good because you don't want this to actually work when it's daytime. Now, motion sensor. So imagine that the light switch is 0, so it's night time, and the motion sensor is on. That means a 1's coming out of here, and then it says the light switch is C is the light switch, so 1's coming into that, and then that would switch on the floodlight. So you've basically switched on the floodlight with the light switch, and then it just only comes on when there's motion detected, which is correct. Tricky that is. That is a difficult one. This is not a difficult one. This is just identify the logic gate from that. So this one, you've got an output wherever there's a 1 going in, that's an OR gate, and this one, there's only an output when it's a 1 and a 1, so that's an AND gate. Drawing the symbols, the correct symbols into this diagram. So the logic system is P, A or B, and not C. Not C. I'm thinking that's going to be the triangle with a circle for not. What about A and B? A or B. So that's going to be an OR gate, and then we've got an AND in the middle, so that's an AND gate there. See if that's right. That's right. Okay, good. And that's it. Those are the questions that have come up for the last 3 years. So hopefully you'll be able to grab yourself some marks from this topic.